Opa, já estamos ao vivo, tá? Pode dar início.
Posso dar início? Aqui tem que fazer um OK, não? I don't know. Okay. So, everything is in order, we can start. So, well, it is my pleasure to announce the thesis defense of the candidate Rodrigo Rana. I thank the member of the commission, Professor Joris van der Riot from the University of Ghent, Professor Sergio Giardino from University of Rio Grande do Sul, Porto Alegre, Professor Alexander Pinzul from University of Brasilia, and Professor Andrei Mikhailov from IFT São Paulo. I should also thank the substitute member, Professor Nelly Stoilova from Bulgarian Academy of Science, and Professor Moses Rojas from the University of Lavras, Federal University of Lavras in Minas Gerais. The thesis is defense is done in the following way. At first, the candidate, Rodrigo Rana, will give a presentation up to 50 minutes, and without interruption. And after the presentation, the question and answer session will start concerning what was presented in the thesis, and also on the oral presentation by the candidate. So I think if everything is in order, I will invite Rodrigo Rana to share his screen and start his presentation.
Okay, thank you, Professor. Can you hear me well?
Yes, and we can see the screen well.
Mm-hmm. Okay. So I'd like to thank all the professors for being here, participate of this defense. Also, I'd like to thank Professor Tapan for all the work you've done so far, the knowledge shared, and all the support during this time. So my thesis title is Institute to Integrated Superalgebras and N-bit Physics, a framework for parastatistics. My presentation is outlined like this. First, I'll do an introduction and motivation about this work, following to establish a mathematical ground where you construct these graded structures, followed by the parastatistics, the Boolean logic gates representations, and the second part, I will talk about the physical constructions, about detectability, the statistical transmutations, and applications in quantum field theory, and finally, conclusions, perspectives, and some acknowledgements. So, introduction. I'd like to start by saying that symmetries in algebraic structures plays a fundamental role in modern theoretical physics. With Lie algebras and Lie superalgebras, we can see many developments in quantum mechanics, quantum field theory, so on. But can you go further? So in these classical papers, I like to say that Wittenberg and Wheeler bring to us generalized superalgebras, where they define two new types of structures that they call color algebras and color superalgebras. From then, many aspects, mathematical aspects, were developments. So these a few examples. Also the physical aspects, like here. But our context here is to try to understand the fundamentals of these grid structures in general. So without setting any specific end to these to any graded party statistics. So also we try to investigate the detectability of these party statistical systems, right? So to do that, have to establish a mathematical ground. So we start by considering a associative ring of ZT2 and graded operators with addition and multiplications actions defined. So the operators A, B, and so on are associated with the any gradings like this, where this n indicates how many sectors can you have in these graded structures. Like n equals 1, you have 2, and so on. This is the gradings of these structures. The multiplication of this operator satisfies this association by the gradings, given 2, and the gradient of the identity operator does not interfere in the gradient of the other sectors, looking 3. So with this, we have to define a Lie brackets, a graded Lie brackets, which is either a commutator or anti-commutator. Depends on the values of this binary map here that takes values 0 and 1. So it also have to satisfy the graded Jacobi identities, given 5. And just a summary, these brackets define a graded Lie algebra or superalgebra, which is compatible with the ZT2N grading of the ring operators. Okay, so under these conditions here, given 6, you can count the complete list of inequivalent canonical forms from the bilinear maps. So for a graded compatible Lie algebras, you have the trivial case, the bilinear map is 0. So this defines originally algebra. We have also this possibility here, given 8, right? For a compatible Lie superalgebra, we have this expression here for the binary map. And if you count all the possibilities of these graded structures, we have a total number Bn that is given here in 10. And this Bn is model independent. So here's a few examples, setting n to a specific integer. Okay, now I present 2 important definitions for physical constructions. That is, a ZT2N graded compatible Lie algebra is defined by the vanishing maps of the diagonal products. That is, if you have all the products in the diagonal vanishing, that means that we have only commutators. Otherwise, if you have at least one anticommutator, that is one non-vanishing map, you call this a compatible Lie superalgebra. Okay, here's some few examples by setting n to 2. We have 4 inequivalent graded brackets. So this ordinary Lie algebra, Z2 superalgebra that you know, the Z2 super algebra here that the Hittenberg really called the color superalgebra, and here the color algebra, the paper. So you go to any bit by statistics. So the map, the binary map always results in 0 or 1, right? So you associate 0 to commutator and 1 to commutator. For any bit, 1-bit case, have these 2 possibilities for graded structures. And this case only reproduce the boson-fermion systems, right? But if you go further, for n equals 2, we have these structures, also the other 2. And from this, you can construct the boson-fermion system as well, but again in a more possibilities. So we have the paraboson statistics, right? And the parafermi statistics. So what is paraboson? Paraboson is a object, is a particle in the sense that emerges from these graded structures. So a paraboson commutes with themselves and commutes between them. And a parafermion, on contrary, commutes with themselves and commutes between them. And also we have here a exotic boson that commutes with the parafermions. Okay, so the Boolean logic gates presentation. So when you see the bilinear maps that takes values 0 and 1, this reminds me about the digital electronics, right? The Boolean algebra. So you can try to use tools from this area. So first, I try to use the kernel maps to understand better these bilinear maps, which is a diagrammatic method to simplify these logic Boolean expressions, right? In terms of logic gates used in electronics, in integrated circuits and microchips, etc. So, for example, we have here the color algebra and the color superalgebra. And here are some set of rules to construct this kind of map. Basically, you have to construct this table here with the components of the gradient vector being the entries, right? And you use a gray code arrangement that is one bit varying column to column, row to row. And we fulfill this table with 0 to commutator and 1 to 1 to commutator. Right? We group the ones in powers of 2 vertically and horizontally, and we analyze which entry varies between in these groups and associate with AND gate. And between the groups, we associate with our gate. So in the end of the day, we have these expressions. This is Boolean expression here for this case, right? It's similar in form to the bilinear map given before. Here is how the gates works and some symbolic representation of the circuits. Here I presented a known case, right? But you use this to work on bigger structures, bigger graded structures. Here I give a reference about what can you try to use this construction. We should try to use in quantum simulations. Okay. At this point, we establish a set of definitions and mathematical tools to work in physics. So we establish a mathematical arena, right? But what about the physics? What about the physical construct? First, you have to define this coproduct, which details in Majid, in this reference. So you consider ABCD as these Z2N grade operators with these gradients here, with a braided product, where you can define, you can use this braided products by in association with these operators explicitly in this form here, 12, where the influence of the graded structures is given this term here. So use the coproduct to construct multiparticle states. Here's some properties of this coproduct. Sorry. now you are able to construct the physical systems. So you can construct this Z2 to n graded quantum Hamiltonians with this with the Bn inequivalence multiparticle quantizations. First, you have to define this matrix here, right? So for one bit, the creation and alienation operators are given in terms of this matrix here. For n equals 2-bit case, we have this. And can you do this systematically? And the answer is positive due to nilpotency of beta and gamma for any given pair of this creation and alienation operators defines a fermionic oscillator that satisfies this algebra here. Also, you have this condition. And how can you do this systematically? So we have to define the gradients by assigning 0 to n diagonal I and 1 to any anti-diagonal operator y. So all you have to do is define an n and associate all the possibilities of I and y, right? So the n equals 2, example, we have this assigned for the creation operators. Okay, so we can define now a n-bit emission Hamiltonian that is given 23, which is labeled by the position 0, so on. So we can define also the exchange operator for n equals 2, given 24, which the gradients are given 25. Will be important to understand this physical system. But first, you have to construct the excited states, right? So you consider this vacuum, two particle vacuum, given in 26. We apply the coproduct of a creation operator in this vacuum. And at this point, you not see the influence of these gridded structures, right? But if you go to the following, you have the site states of energy level 2, have two coproducts, and here you see the explicit influence of these grid structures by this term here, where this term depends on the commutation and commutation relations of the particles. Okay. So for n equals 2, we have 4 inequivalent break structures, right? So if you count the number of states of the application of the coproduct, we see that at level 2 for boson and paraboson algebras, you have 10 states, right? So otherwise in the fermion and parafermion superalgebras, you have 8. So between them, you can differentiate. But to differentiate between boson, paraboson, fermion, and parafermion requires another observable, right? So use the normalized states, Wij, construct in terms of the site states constructed before, and have this in 29 and 30 for these grid structures, where this index here in R indicates where in the column vector is 1. The rest of the entries is 0, right? So you have the states, but you need a operator to act on them. So you can construct this emission operator y by 1, 2, 2, which is 0 graded. It's important for us that is 0 graded. And you construct them using the standard operators mentioned before, like in 31. So if we apply these to these normalized states, we have as an eigenvalue the +1 for 2, 1 into 4, and -1 for 2, 2 into 3. So from this construction, we can see that is theoretically possible to detect these inequivalent parastatistics. But at this time, we do not know the physical nature of this operator. We know that is their mission, okay, but not the physical nature. How can you know that? And start by present the statistical transmutations of superquantum mechanics, superconformal quantum mechanics. So this refers to Z2 to n gradedly superalgebras, which are induced by the superquantum mechanics operators. So these gradings, these Z2 to n gradings, can be applied for any positive integer. In particular, for this n here, we have the superalgebra of the n-standard one-dimensional supersymmetric quantum mechanics is defined by this algebra here, set of commutators and anticommutators, where you assume the H and Q are emission. So for n equals 1, we have two possible graded structures, two possible inequivalent graded structures, right? For n equals 2, we have these gradients here for the operators and all these possibilities. So we count 6 for 2-bit case. For n equals 4, use the funnel plane to do the combinatorics of these gradient structures. So we have all of these possibilities in count 10, right? For the n equals 8, we also use the funnel planes, and you have 14. Here, just a summary of these results. So until now, we have the possibilities of these systems. What about a specific example? So we start by considering a superconforming quantum mechanical system, right? With the Alfaro-Fubini-Fourier oscillator term. Focus on the case n equals 2. Have this Hamiltonian here, where this term beta have to be greater than minus 1/2. So this term is important because it preserves the spectrum generating super conformal algebra. It introduces a well-defined ground state and discrete energy spectrum, which simplify the analysis of the energy level degeneracies, which is important for us in this example. And it allows the direct comparison between the ordinary statistics and parastatistics, with the main goal of this construction here, right? So if you analyze the spectrum, the energy spectrum of this system, you have this 41, this expression 41, where it depends on beta and gamma and n, right? This leads to a structured energy tower with one guard strength and degree 2 of degeneracies of the following states. But to see the influence of parastatistics, you have to go to the second side states and use the coproduct to construct the states. So here you can see the parameter delta, which delta 1, 1, delta 2, delta 1, 2, delta 2, 1, that takes values plus and minus 1, and these parameters encodes the commutation and anti-commutation rules, which is comes from the graded structure. So this is explicit dependence of these grid structures. So if you apply this to the ground state, you can construct the side states. And if you count all the possibilities for these parameters in the grid structures, have this table here, right? And if you go to the excited states, energy excited states, and look at the energy levels, you can see that at second excited states, we have a difference in number of degeneracy in the ordinary particle systems that is composed by bosons and or fermions from the parastatistical systems, right? That's composed by paraboson and or parafermions. So you can see that parastatistical systems cannot be reproduced by ordinary particle system in this way. So it's a signature of parastatistics coming from degeneracy of energy levels. Okay. This was done to in the way that you can try to do it in a laboratory, right? In low energy physics. But what about the high energy physics? So we try to understand this in using quantum field theory. And sorry. Why should we do that? So it allows exploration of exotic statistics, possible new particle types, and standard symmetries. So these generalizations challenge the standard spin statistics, right, in quantum field theory. So the one question arises from this, that can you go beyond the boson-Fermi statistics while preserving the quantum field theory consistency? Well, to answer that, we have to go to the fundamentals of quantum field theory, right? So one of them is the spin statistics theorem. So from Pauling in 1940, basically he proved that integer spins fields can only be quantized using commutators, and half integer spins using anti-commutators, because the spin is a relativistic quantum effect, right? So, but here I like to see in the Weinberg construction way. So consider the one particle states, study all the reducible representations of the Poincare group, and from this constructed the many particle systems with the asymmetrics, and you have also the Dyson series, and from that we recover the microcausality, which is coming naturally by considering the covariance of the theory. So from the microcausality, we can connect, when you try to construct the fields, the spin statistics comes naturally. So this spin statistics connection emerges naturally as a necessary condition, right? So to try to do that in your case, use the quaternionic representations for three reasons mostly. That is, the quaternionic quantum mechanics extends the complex quantum theory with richer symmetry structures. We have a naturally representation of these two training graded structures in parastatistics in quaternions. And you have a physical potential that we could extend the quantum field theory using these quaternionic models. Okay, first we start by something that you know, that is the bosonic theory, bosonic scalar field theory. For this, we introduce here a minimal quaternionic bosonic representation that is given in terms of these matrices here, these bases. And you can define a scalar field in a minimal representation, right? Given 50, where this tilde phi are component scalar fields. So explicitly for the total scalar field here, we have this representation, which the conjugate is quaternionic conjugate. So with this, you can construct the Lagrangian density, in this case, 3. You can set the metric as this diagonal matrix is here, without setting a signature. Okay, so if you open the connect terms, the connect term, you have this explicitly, and for the mass term, you have this, which is standard. For the quartic interaction term, you have this, 56. Okay. Now for comparison with a parabosonic case, we should set this bosonic representation to a non-minimal representation, because the minimal representation of a parabosonic is bigger. So you consider this representation here for the bosonic case, and now you can work in a parabosonic case to compare with the bosonic case. So you use the same quaternionic base as before, but we additionally introduce this parabosonic structure, given in terms of this matrix here. You can define the scalar field as you did before, given 60, and work on the same form of Lagrangian. And the connect and out interaction terms are analogous to the bosonic case, right? But the quartic interaction term is different. As you can see, this term here is slightly different from the parabosonic and bosonic case. Okay, this result is in a way supported by this work here from Professor Konitsova and her students, Lucas Vasconcelos, where they find a similar effect, but in a non-relativistic regime. Okay, but what about the consistency of this kind of theory, right? So you propose to construct a general operator in terms of the parabosonic structure, right? And it's worth to mention that this operator should be in zero graded sector, because we try to associate this with a measure, right? The influence of the graded structure are given by this term here. Explicitly, you have 66. And if you consider a standard expansion of the scalar field, we have this 67. And if applied to the operator, you have this expression here. And if you consider a commutator taken in two different space-time points, and if these space-time points are space-like separated, you have this commutator vanishes. So this is a hint. This result indicates that these operators construct using the parabosonic structure can at least is a hint that satisfies the fundamental requirement of quantum field theory, right? Satisfies the microcausality. Sorry. Okay. From this, it's worth to mention that most scientific works concerning the paraparticle parastatistics have this the physical realization of these paraparticles as an excitation or ineffective theories. So with this partial result, you try to emphasize the need, the importance to see these paraparticles, these parastatistics in a fundamental manner, like in quantum field theory. Okay, some conclusion perspectives. So we present the lower limits for possible inequivalent graded structures, and we present a explicit expression depending on when, right? We present also a systematical way to construct these graded quantum Hamiltonians. It is without setting in at first, right? We present the construction of these graded structures using the Boolean representation. Also, the tools to understand bigger graded structures, and a possibility to use this construction in quantum simulations of these paraparticles. You show that these ZT2N graded parastatistics paraparticles are theoretical observables and distinguishable by a non-operator, like is the energy, right? So some perspectives is to continue the investigation about the algebraic statistical transmutations. The investigation of new physical models focusing on experimentally feasible parastatistical systems, at least theoretically, but approaching the experimental. Simulations of the paraparticles in quantum computations, for example, and continue to investigate the core of the quantum field theory, the fundamental matter for parastatistics, and to understand if can these paraparticles be possible in a fundamental way. So some acknowledgement, I thank this PPF, all the professors and staff and my colleagues, my grant agency, CNPq, and also our research group that Professor Topan leads. Thank you.
Okay. Well, have you finished? So this is you finish a presentation, Rodrigo?
Yes, yes.
So thank you, because it was really within the time. Thank you very much. Oops, sorry. Just a moment. Okay, so we can start now the questions answer session. So as usual at CBPF, we invite first the professor coming from the farthest place, which in this case is Professor Joris van der Jeugd from the University of Ghent, Belgium. Please, Professor van der Jeugd.
Okay, thank you. So thank you for your interesting presentation. And I also, I must say, I also enjoyed reading your thesis. It was interesting for me to read. Of course, I come more from the mathematical side. I'm a mathematician, basically, although I work also in mathematical physics. So I think some of my questions are perhaps more related to the mathematics aspects of your work. But the first question is, well, maybe not so mathematical, but you at one point you present this n-bit representation in terms of Boolean circuits and logical gates. And I wonder, okay, it's nice to do that, but does it have any advantage over the usual formulation in terms of the graded structures? For example, the computation of these sign factors, for me, whether I do it just using elements of Z2 or these n-bit structures, it seems to be the same. So I don't see much advantage of doing that. So maybe you can reply to this.
Yes, yes. Thank you, Professor. Well, first, I would say that for bigger structures, it's easier to work with these Boolean presentations. And also you have you can go backwards. Like say if you have a graded structure that you don't know the mapping, you can go using this table and found the mapping. And also you can verify if these graded structures is in fact as a2n graded. So in this sense, I think it's easier to work on bigger structures, bigger graded structures.
Okay. So that's clear. Now I have a question related to these 6 cases which appear well in your thesis on page 31 on table 2, and I think on your slide is what was on the slide number 48. Maybe it's easier. Yeah, okay. So so definitely there are these 6 cases, and I also had to check myself, but this is correct. There are indeed these 6 possibilities. But in your thesis, you also write that for the last 3 cases, so 2 sub 3, 2 sub 4 alpha, and 2 sub 4 beta, that the number of generators or the number of elements in your algebra consists of 3 generators or 4 generators. You write this in your table, whereas the first 3 cases you say they have an infinite number of generators. Now, for the case which is in this table called 2 sub 2 beta, so the third case here, can you explain why there are an infinite number of generators in that case for the algebra? Or is it too difficult without having the possibility to write on the blackboard, so to say? Do you understand the question?
Yes, I understand it.
Yeah.
Just a moment.
Yeah.
I think it's a mistake.
Is this case that we are talking about, is the algebra not just equivalent to SQM, so the super symmetric quantum mechanics algebra with index 2? So the algebra that is defined in the beginning of this section.
Yes.
Yeah.
Mm-hmm.
I think it is. So according to me, this algebra has also a finite number of generators, I think.
Yes.
Yeah. The other cases, the first two cases, I think indeed, case 2.1 and case 2 sub 2 alpha, they, as far as I can see, they have indeed an infinite number of
Okay.
generators. Yeah.
Yes.
Okay, I just wanted to check this out. If you would have said it differently, I wouldn't have understood it. Now that we are here, so the next slide 52, just a little bit further on. Now you consider the, yeah. Oh no, maybe 51. Yes. So now you consider all these possible transmutations for n equal 4, which is then the 3-bit case. And also here I can certainly follow your classification, but I am not sure what you mean by this second column in your table, graded sectors split. And for example, the third case here, case 3 beta, what is meant here by 7 parabosons? Can you explain that?
Yes. So this columns here refers to the gradient assignment, right?
Mm-hmm.
So to count out all these possibilities of the gradient structures and particles, use the funnel plane, because in a funnel plane we have to work on the gradients. So all the lines that is connected have to satisfy the association of the gradients, right? And
so this is maybe connected to one of the pictures in your appendix, I suppose.
yes, for sure.
Yeah. Okay. I was just trying to understand. Okay, yes, I was trying to understand in this in your appendix, like on, if I may refer to the pages of your thesis on page 93, you have this this table for the case 3.2, and then 2 pages later, page 95, you have this so-called Fano plane for the case 3.2. But what I did not completely understand is in the table on page 93.
93.
Yeah. Yes.
Here.
Yeah. Yes.
Okay.
In this table, I would say this consists of 2 bosons and 6 parabosons. The first 2 grades, I would refer to them as bosons, and the last 6 are parabosons, right?
Mhm.
Is that, and then, but then in your Fano plane, for this case, you have only 1 boson and 7 parabosons. So either it is a minor mistake, or else there is something which I do not understand here. And you can maybe then explain it to me.
Okay. Let me see that. I call this.
Oh, no, I think the Fano plane is also correct, I think, because you have only 7 of the 6 graded sectors in your Fano plane. Of course, you don't have the 8, you don't have the 0, 0. The 0 grade is not represented in the Fano plane. Eh? So that's why you have 1 boson and 6 parabosons also in the corresponding Fano plane. But I still don't understand where the seven parabosons then come from in the graded sectors split.
Yes, I think it's a mistake, because this don't make sense, right?
Mm-hmm.
From this structure here, we have,
Yeah.
you're right by saying that you have 6 parabosons and two bosons. So it should be 6 paraboson and 1 boson, right? Because we exclude the boson of the 0, 0, 0 sector
Yes.
from the Fano plane.
Yeah. But then, okay, then in the for the graded sector split, if you go back to this table on your transparencies, slide 52, then the slide 51, sorry, slide 51. Yeah, then there is no, then the case 3.2 alpha and 3.2 beta have the same graded sector splits, I suppose. Or else I don't understand precisely what is the difference here.
Well, the Greek letter indicates different assigning of in the Fano plane.
Yeah, yeah. Certainly,
Right.
there is a difference in the last column, the transmutation description. This is clear. This I understand, but I did not understand the difference in the second column here. Anyway, let's go to another question, which is more physical, but so on slide 64, I think. Yes, 64. Yeah.
Mhm.
Yes, so that I think this is one of the most important results here in your work, in your thesis, to have this
Agree.
difference in the transmutations. So it's on the degeneracy of the energy levels that this difference appears between ordinary statistics and parafermion or paraboson statistics.
Yes.
Now, okay, as I said, I'm a mathematician. I have no idea how such a difference could be seen in a particular setup, laboratory setup, or whatever it is. So, do you think this is something which is in the future could be feasible, that some experiment is set up where such a difference in multiplicities of energy levels could be measured, or is it for the moment just more like a toy model?
Well, for this specific theory, I don't really sure because I'm not experimentalist, but we try to show that, well, a ordinary particle system cannot reproduce the paraparticle systems, right? So it's a interest of mine to work in other feasible experimental systems to see that, right? And also, I like to mention that the graded structures seen by the Boolean representation logic gates could be a control systems of these experimental systems, right? So in this sense, I don't think this system, specifically this system, can be experimentally constructed, realized, but I don't know for.
Yeah, I also don't know if as I said, I'm not a.
But we why I'm trying to say that we can in this moment to measure no operator, right? That we measure in all the systems, that is E energy. So it's a strong hint for the construction of the systems.
Yeah. Yes, I think the other systems where a difference was noticed between ordinary statistics and parastatistics, then it was usually the difference was in an operator like the exchange operator you mentioned, which has, I think, not a real physical meaning or interpretation, but at least I think here the operator has a physical meaning. It's the energy. So maybe I think this is for the moment probably the best hope of constructing a real situation where this difference could be measured once.
Yes.
Okay, that's all for my questions. Thank you.
Thank you, Professor.
Thanks, Professor. Thanks, Professor Van der Joogde. Then I will also have some comment, but I will say later. Now we pass to the next professor, and I trust the computation presented by Professor Pinzul. He mentioned that Professor Giardino come from the furthest place from Rio de Janeiro, because Porto Alegre is further than Brasilia from Rio. So, Professor Giardino, please
Hi,
invite.
good morning to everyone. Could you listen to me clearly? Are you hearing me well?
Yes, yes.
Yes,
Hear very
Professor.
well. I hear very
Yeah.
well.
Well, thank you. It's an honor to be here. So, first of all, I would like to say that I will concentrate my questions to more general questions, where I will not emphasize technical points, because I'd like to discuss more general ideas, okay? So, first of all, I would like to say that I consider the introduction of the paper of the thesis that I mean, I'd like to say that, for example, if you write an article, it's enough to mention some recent references and to consider a specific point that you are interested in. And it's enough. It's enough to motivate your work. But if you are writing a thesis, I am expected to, because we have more room or more space to describe, a more, let me say, a more profound description of the area of the subject are you interested in. So if I look at your introduction, maybe it's not so clear the history, the historical background of the subject you are describing. So the first question that I would like to ask you, it's a very general. How could you localize your work within the line of research of Professor Francesco Topan? Could you understood?
Sorry, can you repeat the last?
Could you give us a brief idea of the kind, how could you localize your work, your research described in your thesis within the line of research of Professor Francesco Topan?
Okay. Well, like I showed in the beginning, I put our work, our paper, in the with three another papers, right? Two by Professor Topan that he showed how to construct the multi-particle systems and the difference in the grid structures from ordinary particle system. And also a paper that was published in the beginning of this year in Nature, that one of the structures that the work is a grid structure. So I think the relevance of our paper and my thesis, I put this in this sense, this importance. Also, like I'm showing right now, this important result, right? About the difference between a ordinary particle system and a paraparticle system.
Well, maybe I have to clarify. If
Okay.
sorry.
No, please continue. Sorry.
I just want to say that, correct me if I am wrong, but I understand the work of Professor Topin basically concerned with the interplay between geometry and further algebraic structures. So if you build a space considering the geometry and further algebraic structure, you can discuss which kind of physics can be described in this work, this background. But from a mathematical point of view, you can describe the consistency of this background and which kind of physical elements can be found there. But from from a physical point of view, this is not enough. You have also to build real physics to have representations of algebra, okay? But everything that you have done in your thesis, you have described spaces, you have endowed them with algebraic structures, you have described physics, and also you have built representations. So your work is, from my point of view, a clear example of the line of research of Professor Topin. Okay, am I right or not? Do you agree with me?
Yes, but I think different from Professor Topin, I think Professor Topin is more mathematical than me. So, well, I don't know for sure if I agree totally, but you have to define what a real physical system is, right? Because I don't know. I think we work with a set of physical constructions. So maybe it's more is much theoretical, but I mean it's a beginning to work on these grid structures for a experimentally way. I don't know if I understand your question in this sense, Professor. If you
Well, sure. I'm just trying to situate your work within a bigger context. This is what I'm trying to question you. If your idea in a more popular way, I'm trying to understand if you know what you are doing.
okay.
Okay. This is
Okay.
just if you can, we can. I started to saying that when we try to write a paper, we can just look at specific points and very small problems to solve, maybe
Mhm.
without looking at the bigger context of our work. If you are doing science, you have to look at this wider context, not only to your specific research. What I mean, the difference between doing research and doing science. Okay,
Okay.
you agree?
Yes. Well, I have a point of view about that is that you use mathematical physics and theoretical physics uh, as a flashlight leading the way to work with physics, right? So we can see, we can realize the physical systems by studying theoretically, right?
Sure.
And one of the main goals of my thesis, of my PhD, was to work in these physical constructions about the systems, these graded systems, and specifically about the detectability. And for do that, I have to understand all the fundamentals of these graded structures in a general way. And from that, uh, we could construct a set uh, of tools to work on these graded structures that we not expected. So I think this is how research works, right? You don't you found some results that you not expected, but it's a way to look uh, how can you construct the physical systems from the mathematics.
Sure. Okay. Just a question about the history of the subject. I was very quickly looking at the literature, and I was trying to understand whether the subject of graded algebras, which was the first when it was introduced, and I found some work, maybe you know, maybe not, but the article which the authors are Leonard and Moore, which is from 1965. I don't know if it is important. I just only found it quoted within your references, but you have not quoted this. This is the, if you remember that I told you that I cannot build the historical view of the subject. It's because like this, you have quoted some more recent references of the subject.
Yes.
It's not important. I know that it is a matter of taste in many cases, which reference you have to quote, okay? I'm not saying that you must to quote the first references, but maybe it's not so easy to understand if you write your work for someone who is not an specialist, an expert on this subject. It will be more difficult to understand your own work. If we write a thesis, we have also to think of people who are not so close to the subject. Okay. I know that's also a matter of taste, but I just want to point out that you could, in the future, or maybe think of your own work in a wider context.
Mhm.
Okay. So that's found also in the introduction, when you talk about the para statistics, the references
Mhm.
also do not mention the original idea. I found in a quick search in the literature that the original idea comes from a paper of Green in 1963, 53, sorry. So it's not so easy to understand the context of the subject from your thesis. Okay, maybe it's easier for someone who is more well acquainted to the subject. Okay, would you like to say something about this?
Yes, I try to connect all the basic uh, historical facts, but was not the focus on the introduction. As you can see, the introduction is is big enough by not considering this point. But I can modify to include some historical context uh, to give more sense about the thesis.
Just one small typo. In the paragraph 3 of the page 1, there is a missing reference. You can find maybe you have also observed that there
Yes,
is
yes,
a missing reference there.
yes.
True? Well, let us go to the chapter 2, to the color superalgebra. Just a question. This name, color algebra, do it have any relation to the QCD or to the
No,
quantum number? Why this name?
why this name?
Maybe you don't know, but it's not important. It's just a curiosity for me.
Yes, I'm not sure. This term was called by the Rittenberg-Wheeler in the article for 1978, right? So they consider as Z2 graded systems. So they present these two graded structures and all the constructions from this. Also have a mathematical paper about these these first papers about these graded structures that is from Schoenet. It's an interesting paper to look.
Also, it's also maybe not very important. For example, in paragraph 1 of page 4, when you introduces the exotic commutation relation in this first paragraph of page 4. So, could you find it?
First paragraph of page 4.
Sure.
Excuse me, Rodrigo,
Oi?
could you maybe share the
Thesis.
thesis, yes, would be better. Yeah.
I
Okay.
just trying to find it here. Just a moment. It's in the first paragraph of just in the beginning of the chapter.
Mm-hmm.
For example, you talk about among these structures, scholars superalgebras generalize the concepts of split algebras and superalgebra by
Mm-hmm.
incorporating graded symmetries and exotic commutation
Okay.
relations. Okay,
Mm-hmm. Okay.
so again, to someone not well acquainted to the subject, it's not obvious what are exotic commutation relations.
Okay.
So uh, if you are not, maybe if you are of the field of the, but if you are looking for a thesis to learn about the subject, you will be in a difficult situation here. Okay. Also, if I consider in equation 3.9 in chapter 3, sure. So you can see also the symbol of the floor function, but if you do not have this concept previously, maybe it's obvious, but from physicists, I believe that it's not obvious to everyone what is a floor function. So this is a kind of thing that could be better explained. So if you are really interested to be understood, okay, let's go to paragraph 3.2.3 when you introduces the Karnaugh map.
Two.
3.2.3. Previously, earlier.
Okay. 2.3. Okay.
3, 2, 3. True.
Okay.
There.
Mm-hmm.
3, 2, 3. So there you introduces the Karnaugh map.
Mm-hmm.
So, and you mentioned that it's a resort to classify non-equivalent algebras. Okay.
Yes.
So it's a very important point because you have to decide which are the physical classes concerning the non-equivalence. Okay. So I just want to ask you something about the generality of this technique. If you could apply it to the simpler case of only Bose-Einstein statistics, could you use this map? How can I, let me say, inquire if this technique is well suited to this problem? Because if I can apply to a simpler problem, I can say, so the technique is working well. But you are applying to a more sophisticated case.
Yes.
The question is this technique well suited to this kind of problem?
Yes. We did that, but that not making much sense because the Boston-Fermi systems can be reproduced by the if I set n equals 1, so we have two graded, looking from the graded structures, we have two possibilities for the grading, right?
Right.
So the ordinary algebra is from this point of view of Boolean logic gates is simple null. So you don't have the Boolean representation in this is trivial. In the case of Z2 graded superalgebra, which is the other graded structure, is a AND gate. It's part of uh, the mapping, right? So you could use this on the boson-Fermi systems, but I think the goal with these representations is to work on bigger structures.
Sure. Okay. Now, I want to go to section 355. Just a moment, I'm just going to go to here. Sorry. So my question is, so here you are talking about physical applications, right? And so, but again, there is no reference to this kind of physical application. In this section, you are only talking about maybe future directions of research or not.
Sorry. Yes, in a sense, why how can you use these equivalence classes to construct the physical applications?
So,
It's like a introduction for the why do you what you do next.
sure, sure. And so in chapter 4, in section 403, okay. So in item 2, the omega is zero graded. So,
Yes.
Yes, but I have not found the explanation why it is. Is it a choice or is it the only option?
No, it's because when you talk about the measurable, the observables, the operator should be in the zero graded, because it's the grade that we put the bosonic quantities, right? So if you talk about observables, you have to put this on the zero graded.
So if you are not zero, what happens? I'm sorry.
It's not a measurement. It's not a real number in this sense, if you talk about the observable.
So it is related to some kind of ermeticity of the problem, or not?
Yes, in the sense. The zero guarantees that you have real eigenvalues for the operators, right? So we put them on this sector.
So
If
in
you talk
fact,
about the observables.
so in fact, we are considering a constraint of the problem.
Yes, in this sense, if you talk about the observable. If not, that's no problem to put on another graded sector.
So I'm gonna ask you because when we consider Hermitian quantum systems, we are always talking about stationary systems. And if we consider non-Hermitian cases, we have to understand that we can find dissipative problems, physical systems, or evanescence, non-conservative processes. Okay. In section 404, it's just a small consideration. Yeah. Okay. So in this first paragraph, you mentioned equation 5.1, which is in the future of the thesis.
Okay.
So it's difficult to consider. It seems that understand you cannot write this kind of thing. Okay, we have to mention only what is in the text of the work. So now I would like to go to section 4011, please.
4011. Okay.
Let me see from my notes, just a moment. I just want to ask you, the application that you are considering can be understood as the construction of an algebra of creation and annihilation. Sure?
Yes.
So, okay, this is just a small question that I had. I have no question here. Let us go to chapter 5. So you are talking here on the statistic transmutation.
Yes.
This is the model to be applied that you applied previously to the quantum mechanics. So you'll be discussing in a more general sense. My question is, to me, it's not clear what you are talking about here on detectability of parastatistics. Are you talking something about phenomenology or not?
I'm talking about ways to measure these paraparticles and differentiate between these paraparticles and ordinary particles. This is what I mean about the detectability. A theoretical way to do that.
So when you say detectability, you are talking to calculating eigenvalues, expectation values, or not?
Yes, yes.
Sure. Well, okay, clear now. I have not understood that. Okay. So just want to see in chapter 6, I'm just I have to find a bit, just a moment, in the applications in quantum field theory. I will find I am interested in. Sure, I have not found, but the idea that I would like to ask you is the following. If you consider the mathematical framework that you are applying to your work, we can understand as a mathematical tool to solve a problem, or we can understand as a way to build a novel theory. That's, for example, I will give you the example of my own work. For example, if you consider the generalization of quantum mechanics, if the framework, the mathematical framework, is not general enough, we cannot solve, for example, the difficult problems, for example, the quantization of gravity. Maybe if the theory is not mathematically general enough, it's impossible. So you have to introduce a novel mathematical structure there. And however, if the mathematical structure is general enough, you can actually only find a mathematical method to solve the problem. For example, in quantum mechanics, normally you have the usual theory in the complex Hilbert space. But maybe you have to use a more general space, maybe a real Hilbert space, maybe a quaternionic Hilbert space. And so if you can solve a problem in these spaces that are not possible to answer in complex spaces, you have to generalize the theory in a mathematical way. It's not only to find a mathematical method to solve within the complex Hilbert space. Am I clear?
Yes, yes.
Could you understand?
Mm-hmm.
So, in your own work, do you understand it as a mathematical tool to solve a problem, or you understood it as a novel mathematical framework of a theory?
Well, I think that you could develop a nice set of diagrammatic methods to work these graded structures, right? Using the previously existing mathematical tools. I don't think we developed a new mathematical, a new I think that we we work more on the mathematical physics, focus on the physics, right? And
because now I find what I'm looking for in page 59 when you write the historical and generalized context, and there, yeah, there, and you are talking about Lorentz symmetry. So, if you are trying to approach the Lorentz symmetry using your mathematical technique, maybe it's only a mathematical technique to solve a problem. But maybe you have a new theory that cannot, that is more general and can solve, for example, with no broken and unbroken Lorentz symmetry. So it's not clear in principle if the usual theory can describe broken Lorentz symmetry. So I'm only arguing you that maybe you can think or not of your theory as a new theory, or only a mathematical method to consider this kind of problem. Well,
okay, I understand the point. Well, I'm not sure what I mean think about it, but what can I say that is we developed for example a systematical way to construct the physical theories using all these representation. So it not use a new mathematical construction, but you give in a sense, in a physical sense, to construct using these grid structures. Also the statistical transmutation, which is leads to an important result. So I think it's debatable what the importance in a mathematical or physical sense.
sure. I have maybe a final question. Considering you have built several Lagrangians using quaternionic numbers, but correct me if I am wrong, but you are not considered the equations of motion that can be built from these Lagrangians, okay?
Not here, but this last part of the thesis is a work in progress. We have more results that are presented here, but it's not finished, and you don't finish to work on this equations of motions. You're right.
But just one question: if you consider maybe quaternionic valued Lagrangians, if you are using let's say Euler Lagrangian equations which use quaternionic variables. For example, if your field is a quaternion, and in this Euler-Lagrangian equation, you will consider the derivative in terms of this quaternionic variable that is your field. Sure?
Okay.
But it's the quaternionic functions are only linear functions. So it is very restrictable, the kind of Lagrangians that you can use. You cannot, it's only trivial things that you can do. So I have not found the Euler-Lagrangian equation and the equation of motion now. So, but I'm just trying to tell you that maybe you have to consider with more care which kind of equation of motion you are interested in the future. Okay.
Okay.
So I have no more questions. I would like to thank you again and to congratulate you with your work. I know that is a subject that is difficult, and also to let me say to have a good relationship with the editors of journals. And so again, thank you so much.
Thank you, Professor.
Thank you, Professor Giardino, for your observations. We also would like to ask if you can send the references that you were mentioned, the reference from the 60s. Thank you very much. And now we pass to the next member of the commission, who is Professor Alexander Pinzul from Brasilia.
Hi.
Please.
Thank you. Thank you for presentation. I especially appreciate that it was in time, even slightly shorter than time. I mean, and the second point about presentation, you had like 89 slides, and now I'm very deeply curious what is in the last 4 slides, because you stopped at 85, I guess. I mean, I'm just kidding. But I mean, if there is something interesting there, I mean, please show. Okay.
Here.
Because that was very intriguing. Okay, so anyways, so mostly I will comment on the text of thesis, so you can go back to thesis. So the comments are mostly quite technical, meaning, so could you go just directly to page 4? So I will make several comments and you will understand more or less. I mean, so I will not like keep on going, like page 4. 4 meaning of the text. Yeah, so here. So meaning that you have to decide on the level, on the rigor of the presentation. Because I mean, this part, I mean, like, is more mathematical, right? I mean, part 2 and all this stuff. I mean, so because of that, for example, like in the equation 2.2, so in 2.1, you say, okay, it's gradient set G. So to grade the vector spaces, it's enough just to have a set. I mean, so but to grade algebras, that set already should be at least a semi-group. because you have addition there, right? I mean, in the set. I mean, so the set does not have addition. I mean, so my point is that it's a minor point, but because I mean, like it's like mathematical part. I mean, you should like either stick to more mathematical thing, because I mean, otherwise, if G is just a set, 2.2 does not make a sense. Make sense because G plus H on the right hand side of 2.2 is not defined in a set, right? Right? I mean, so you need a semi-group for that. I mean, so then next page, as I said, I mean, several points about yeah. So so you define this graded commutator in 2.3 really already in the universal in associative algebra. I mean, so but then the Jacobi is not a requirement; is a consequence. Jacobi is a requirement only if you define formally. I mean, so because like in Lie algebra, Lie bracket is the product in non-associative Lie algebra. Then Jacobi is the consistency condition and all this stuff. But if you define Lie product as a commutator in associative algebra, you can derive Jacobi, right? I mean, just plug in the commutator, opening all the commutators. So in this case, graded commutators. If you plug 2.3 in Jacobi, I guess you will have identity. So further, when you define it, you define a graded commutator really as a graded commutator. And then, of course, Jacobi is required as a part of the definition. I mean, so, but here at this point, I mean, so this is again on the like rigor, like you should more or less. I mean, then page 8. I don't know. I made some comment on page 8. I don't remember what is the comment because I wrote just pages for myself. No. So here it was just that in some sense this section kind of repetitive in a sense. I mean, so you just repeat the same things which you defined before. I mean, so maybe just like do this definition, as I said, but not in the universal enveloping, but just like do this definition and don't repeat it because it seems really like a copy paste from page 4 in some sense, or page 5. I don't remember which one. Page 10, I guess. Page 10. Yeah, go slightly down. Logical operations. So these logical operations not in Z2n. You really define Boolean on Z2. Then you use that for Z2n to define the pairing. But these are for Z2 because we also always say that, okay, so alpha or beta is just like 0 or 1, 0 or 1, right? I mean, after that, you extend this, I mean, use those logical operations for Z2n. When you use like scale product there, but Boolean operations, or XOR or not, I mean, they you really define them for just for Z2 for here, right? All those alpha 1, beta 1, they're elements of just Z2, or not? What in this part, in this first paragraph, what element is in Z2n? I guess neither.
Yes, okay.
Because I mean, you define the point is that Z2 elements of Z2, they're like elements of the vectors in Z2n. So first you define Boolean operations on Z2, and then of course I mean you use those. So for example, if you go slightly below the last line, so here you see that is for Z22. Why? Because you have alpha 1, alpha 2 is kind of like a you have two element the vector in Z22, but the Boolean operator, by the way, here I guess you should not use dot because you defined actually a wedge. So what is dot in this sense then?
Dot is the other symbol for AND gate.
Right. So that's another comment. I mean, so you should stick to consistency in the
Okay.
definitions. I mean, right? Because I mean, so here, strictly speaking, because you just introduced AND with a wedge.
Yeah.
And the next line, you stop using that and use dot. I mean,
what I try to do here is to use dot to represent the logic gate itself.
no. I understand.
Not the
Then you either have to like to say something about that we will be interchangeably using that and that, or stick to one notation and all this stuff. I mean, so and plus on this paragraph, in some sense, I mean, it's kind of clear, but no. Go up and yeah, here. But strictly speaking, because that looks like a definition of all the logical operations. Neither of definitions, except the last one, I guess, is finished, because you say that, okay, so AND is alpha 1 wedge beta 1 equals 1 if both alpha 1 equals 1, beta 1 equals 1. And if not,
okay.
then you should say that
Flat
alpha 1
zero.
wedge beta 1 is 0 in all other cases,
Okay.
When you define OR, the same thing. Alpha 1 inverse wedge beta 1 equals 1 if alpha 1 or beta 1 equals to 1, and if not. So I mean that if you start definitions, finish them in some sense. So then the next page, I think, or I'm really misunderstanding, or the page, the table is messed up. I mean, so take, for example, line alpha 1 0 alpha 2 1 beta 1 1 beta 2 0. So it's line 0 1 1 0 0 1 1 0. You say that you say that the result is 1. I guess it's 0, because I mean 0 times 1 is 0, 1 times 0 is 0, 0 plus 0 is 0 in several places, right? I mean, so I mean, it should be alpha 1 times beta 1 plus alpha 2 times beta 2. It's 0 1 plus 1 0. It's 0.
Yes, you're right.
And you can see that into this kernel, the following section, and several lines. That was just an example of line which I just like. So in this section, so for example, you define like that you have to take adjacent ones and all this stuff, and so probably not here. I mean, my point is that because I mean this table, the current table, based on that table above, I think it's just like copy. So in this table also, I think the same type of mistakes, especially if you compare with Appendix C. Please go to Appendix C. I think in Appendix C, these tables are correct. So here, just go slightly down, down. Yeah. So no, now up. Yeah. So now here, I think ones and zeros are in different places, in correct places. I mean, but what is wrong with Appendix C and D? I guess. I mean, so look carefully at the numeration of the formulas: C0, 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 and indeed the same thing. I mean, so it's kind of like numbering sucks. Вот. Okay. So, okay, so that's the main point. I mean, so about this section, I guess that I agree with Joris, if I understand what he meant. I think this Boolean part, first of all, is slightly messed up. I mean, on the level of definitions and all this stuff. For those who does not know anything it will be not very much useful, because I mean, it's very difficult to understand how those diagrams, for example, constructed, I mean, and all this stuff. I mean, so maybe if you want to keep it, I mean, probably you should keep it. I mean, so maybe give like more specific example, like more detailed example, how it's really constructed, and at the end of the section, make it more obvious that this is really useful. Maybe not like presenting like concrete example or demonstration, but at least in words, you should say more like why this is not just like rewriting the same thing. So why this is really useful. So I almost done with comments about the text. So could you go to page 20? Yeah. Yeah, equation 4.8. I mean, without parentheses in front, around 1 and plus, well, that equation is wrong. So, because I mean that equation is obtained from the fact that coproduct is a homomorphism, and then you use a squared equals to 0, but then you have two cross terms. One cross term comes with 1, another cross terms with minus 1 to the degree of pairing. I mean, so this combination of ones should multiply that braided tensor product. I mean, not one. I mean, if you just multiply, you will see that there is no way that you will obtain just like 1 plus tensor product. Just go. So 4.7. Take square of 4.7. What you will have? You will have 1 tensor a squared, which is 0. Then you will have a squared tensor 1, which is 0. And then you will have two products. I mean, 1 tensor a plus a tensor 1, which will pick up the factor of -1. And the second one will be a tensor 1 times 1 tensor a, which will not pick up the factor. Why? Because the gradient of 1 is 0. So you will have two the same tensor products, one with the trivial phase, another with the phase defined by the by the parent. So my point is those 1 plus -1 should be in parentheses. This is a factor.
Okay.
That's why you have the conclusion afterwards that, okay, so if parent is 1, this is 0, because it will be, the factor will be 1 minus 1. Because, I mean, if not, and parent is 1, you will not have 0. You will have 1 minus a tensor a. So I'm pretty much sure there are some small mistakes like that. I mean, so my advice, I mean, like, go through very carefully, like checking all the formulas and all this stuff.
Sure.
Okay, so page, for some reason I wrote for myself page 21, 22. I don't know. Could you go to page 21, 22? Go to 22. Maybe 22 will give me a hint why. So now I remember. So you see, go to 21 now, and I remember. So you start like, okay, so example, case n equals to 1, case equals to 2, then you write section general construction, and then you again write case n equals to 3. So it's kind of like discontinuous, like you particular case, general construction, you continue with particular case. You don't need n equals 3 because it's already a general case. It's pretty much clear what is the structure. So 4.18, 4.19, you can calculate really from the general construction. N equals 3 is not very much illuminating compared to 1, 2, because you just define the general case already. So, and maybe it's useful to include, because what I understand, so like in usual fermionic oscillator, the system of usual fermionic oscillators, the anti-commutators between oscillators of different types, like I and J, they have this factor delta ij. My understanding that here it will be not in general delta ij, right? I mean, but it's not difficult actually to calculate it from the fact that I squared equals to 1, Y squared equals to 1, and anti-commutator of gamma and beta is 1. So you can write actually a general anti-commutator not just for I, but really ij. I mean, so on the right-hand side, it will be something very, very simple. And related question, actually, so this is the last probably, just go to the Hamiltonian, 4.22. Why it's defined just like with 0, 0? My understanding, because exactly from I squared equals to 1 and Y squared to 1, that instead of 0, you can put any index there. It will be still exactly the same. Because, I mean, A has the structure like Y, I, Y, gamma. Conjugated will be also the same Y's because, I mean, they're Hermitian, but beta. So when I multiply, all these parts with I and Y will be 1, 1, 1, 1, 1, because, I mean, I squared equals to 1, Y squared equals to 1. But in the place of beta gamma, it will be, for example, beta gamma, then plus, I multiply in the different order. Everywhere in the places of Y's and I's will be 1, 1, 1, 1, but in the last place will be gamma beta. So when I take the sum, independently of what is 0 or I index there, it seems it will be exactly the same expression all the time. I mean, so it seems that you can have like more symmetric, in some sense, definition of the same Hamiltonian, like 1 over n and the sum over all oscillators. In some sense, it will be exactly, but it will look, because in this case it's not clear like why to prefer 0 index, for example. I mean, so why not to take 1, 2, or whatever? I mean, once again, maybe I just misdid my calculation, but it seems, once again, how you calculate the anti-commutator. You multiply A dagger with A, you multiply plus A with A dagger. When you do multiplication, all this non-trivial part will square to 1 all the time, because it's made only of I's and Y's. So check, I mean, so if true, I mean, I don't know whether it will help, but at least it will remove some obvious question, why to define 4.22 with 0? Why you picked one type of oscillator? Some misprint which I noticed, equation 4.33. Okay, yeah, I think the first x without n. The second
yes,
x is with.
yes, right.
So that's how far I went carefully. So I don't have more comments about the text, but I have a couple of just questions, more general questions. I mean, so you have some generalization of this the Alfaro-Fubini-Farlan model, right? I mean, this quantum mechanics, conformal quantum mechanics, DAFF, right? I mean, you talked about that. So I don't remember very well, but I mean, so when we were talking, I recall that in the usual this DAFF model, kind of like a problem that they don't, though the model is conformal, like on the level of the operators and all that stuff, the grounds, there is no conformal invariant, there is no SO21 invariant SO21 invariant ground state. Just there is no, I mean, so if you try to construct the ground state, I mean, so from the Hamiltonian and all the stuff, I mean, you see that it the ground state does not have the conformal invariance. But if you consider correlators, they do have conformal structure, meaning that they have this correct behavior 1 over t minus t to the degree blah blah, and that kind of like indication that okay, so this is still like having conformal behavior. So it's like I'm not expecting the answer, but maybe you know the answer. I mean, this generalization, does it change somehow the situation? Because I mean, clearly the spectrum should be changed. Maybe you have now a ground state for this generalized Hamiltonian, which is respecting conformal invariance or something like that. I mean, so I mean, no pressure. If you don't have an immediate answer, like you can think about it. I mean, so maybe the question does not make much sense and it's obvious. I mean, all stuff. I mean, so.
Well, I'm not sure if I understand it completely, but
so let me repeat quickly. So, of course, I mean, conformal invariance, meaning that there are some generators, some operators of that conformal invariance, I mean, which generate conformal symmetry. Then you look for the Hamiltonian for your dynamics. You find the ground state of the Hamiltonian. I mean, just like you apply those generators of the conformal symmetry, and you find that they do not kill the ground state, meaning that the ground state is not conformally invariant. So typically, if you have some symmetry, typically you expect that vacuum is the most symmetric one. I mean, so it respects the symmetry. I mean, so in quantum field theory, you even have like some kind of like Higgs theorems, blah blah, and all this stuff. I mean, that just translation invariance, for example, in most cases is enough to fix the vacuum. It's the only translation invariant state. I mean, so here actually the ground state is not conformally invariant. I mean. But if you start calculating the correlator, the matrix elements of some operators, so correlators, I mean, like, then you will see that they do have an expected behavior. Because I mean, in conformal field theory or conformal theory, you know that the first correlators, the form is completely fixed by the conformal symmetry. So I mean that you don't have to calculate, in some sense, that they the form of the correlators, it's an indication that you do have conformal symmetry. So it's, as I said, I mean, so typically it's like 1 over, so in one-dimensional case, so it's quantum mechanics, 1 over t minus t prime, it's like t and t prime, the times of the first operator and the second operator for which you calculate the correlators. So it's like 1 over t minus t prime to the conformal dimension, or so, something like that. I mean, so 3-point correlator also you can calculate just purely from that. So I mean that correlators, they do have conform, but the ground state is not conformally invariant, and that kind of like not exactly a problem, but this is a very specific point of this DAFF model. So my question was, because you extend your model. So Hamiltonian is extended. I mean, so like spectrum probably will be different. So maybe you do have a ground state which is conformally invariant or stuff. I mean, so that was the question or comment. Or
okay. Don't know exactly if it's conformally, but when we construct, we saw that we have a well-defined ground state.
Yeah, so I mean, clearly it does have a ground state. I mean, so meaning that my point is that now you can check whether it's conformally invariant. A simple check. I don't know whether it's of any use for anything, but I mean, at least it will be like some improvement compared to the original model. I mean, so that, okay, so we do have a conformally invariant state or something like that, or we don't. And the last question, really the last, I'm not very good with physics, but I mean, so this is like the most physical question which I can come up with. I mean, so in this approach, like it's not even what would you expect. I mean, so the point is the following. So there are examples in other models of like kind of, let's say, twisted statistics and all this stuff. For example, non-commutativity, you can have like twisted statistics and all this stuff. There is not the same type of twist. I mean, so they more comes from like Greenfield twist and all this stuff. It does not matter. But I mean, there is a parameter which controls that, for example. And if I would like to have some physical questions to ask, I mean, so the questions will be, okay, so what kind of experiments I should do to put some bound on that thing, I mean, on the parameter of non-commutativity. So typically those bounds, I mean, so mean that I really kind of like give a model, toy model, and say that, okay, so if in that toy model I will do that, I mean, so then comparing like to some hypothetical, I'm not saying like about real experiments, I know nothing about that, but I mean, in principle, if I would measure that, then I should see that, and that will give me a bound. So if I don't see that, it means that parameter of non-commutativity definitely is less than that one. So, and at the moment, I mean, the bounds on non-commutativity really push like in such to such values that it is impossible to measure. Or like, for example, like also like generalized symmetry, like supersymmetry. There also we know, okay, so we don't see all those super partners and all the stuff. So it means that we have a bound on the scale where the supersymmetry is broken. So in this approach, what exactly could be bound, and what is the meaning that what kind of because I mean definitely like we kind of like on fundamental physics, I don't think that we see that, right? I mean, so what kind of question we should ask, and what kind of bounds we should expect? I'm not saying numbers, I mean, but bounds on what? Like so meaning that that's really probably not naive question, because as I said, I mean, so but what kind of experiment should tell me that, okay, so no, I don't see it. It means that something, because if I don't see something, it means that typically that something is small, or vice versa large, like so inverse is small. So scale is the symmetry breaking scale is large. The non-commutativity is small. So what here is should be small or large, due to which we don't see it, or it's very difficult to see.
I think we could try to understand a series of physical systems in, for example, in low energy physics, and try to give a graded construction about the systems and try to compare with the observables. I don't know if you can do that. I know that we can try to simulate these systems. And this talking about the in low energy physics. About the high energy, I think it's a lot more to investigate. We found a difference on the interaction in Lagrangian level. We don't know yet what that means, but I think you should research this. And well, I don't know a specific bound of this.
No, specific no. So let me just like to finish, like, if I understand correct. So strictly speaking, like, if you would come up with some more or less like realistic model based on this, I mean, so you should expect to see some processes which otherwise would not exist, or what I mean. So, but the probability of that process will be like very small, and the fact that you observe that process would tell you that yes, I mean, so we do have this generalization and all stuff. Is that more or less the direction? I mean, like, to observe some, or it will be reflected just in like some like tiny correction to already existing like values of something. Because typically, my point is the following. So typically, the symmetry questions are related to the question, okay, so I compare an exact zero to something. That something could be very small, but it's not an exact zero. So that's why it's much easier to detect processes related to existing symmetry or breaking symmetry and all this stuff. Because I mean, typically you're not talking about some tiny corrections. I mean, they tiny corrections, but they tiny corrections not to some numbers already, but really to zero in some sense. I mean, so anyways, I think once again, it's not really about physics, but more like about the motivations, like what to expect and all this stuff. I mean, so but otherwise, I think yeah, I mean, it's kind of a difficult subject, so it's not that easy to grasp the whole thing, and I think you grasp it like good enough to really like have some control and all this stuff. I mean, so good job.
Thank
Okay,
you.
so that's all on my side.
Thank you.
Thank you, Professor Pinzul, for your observations. Were very the point. Signalization of the typo for 8 and others. So it was a really very careful analysis. Thank you very much. And now, last but not least, I will invite Professor Andrei Mikhailov.
Thank you, Francesco. Thank you for me. So
can you hear?
Can you hear me? So my first question is, can you explain to me, Rodrigo, what is the transmutation, statistical transmutation, you call it? I could not, so it's a major defect of the thesis. You talk about this transmutation all the time, but you never define it and never explain what it is. So it's like your major result, or at least a major topic of your thesis, and you do not really define it.
Yes. So this statistical, this algebraic statistical transmutation is, I think it's a method to give all the possibilities of gradient structures in relation to the excitations, the paraparticles and particles that comes from this.
Slower, please. I don't understand. You're saying too fast. I'm not able to grasp it.
I'm sorry. The algebraic statistical transmutations refers to the construction, the about all the possibilities of excitations that come from these graded structures.
Excitations which come from graded structures, what it is?
Particles excitations. What
What-
kind of particles can we
What do you mean by particle?
like
What
ordinary?
excitation of a particle or
No.
which are like particle or what is it?
Particles are as excitations from these graded structures.
Particle
So
excitations from graded structures?
yes, what kind of particles can we build with these graded structures?
How can you build particles from graded structures or with graded structures? You like use it like a tool to build particles?
Sorry?
How can you build particles with graded structures?
Well, we see the how these particles works in the I mean, we see from the commutation and commutation relations and how they interact with each other.
Commutation and anti-commutation relations of what?
Of the of the structure that we are considering. So if you have the
relation of structure.
No, these commutation relations defines a structure, a graded structure.
Relations of what? Which commutation relation? In what context?
I don't understand your question.
I asked you, let us return. I asked you what is statistical transmutation. Let us start over.
Yes. So this is in this way a method to set using the super quantum mechanics algebra to set the supercharges in these graded structures, and by doing that we can see.
Speak slower. I cannot. It's too fast. Can you write something, or I mean, I was not able to understand the main concept of your paper, the main construction. Not the paper, sorry, the thesis. So is it true that you are defending on a single published paper?
Sorry?
Are you trying to defend PhD thesis on a single published paper with 3 co-authors?
I think I don't understand your question.
So how many papers you published?
From the thesis, this one.
Okay, so it's kind of unusual that there is only one published paper and with 3 co-authors. So I'm trying to see if you have good command of the paper, if you understand it.
Yes.
Okay, that's a good question. That's a good answer. So, and one of the concepts which you introduced in your paper is the concept of statistical transmutation, but you never define it. So at least you now explain to me that statistical transmutation is a method. Can you outline the method? So, or maybe give a simple example. What is the simplest example of this method?
Well, if you use the we take the super quantum mechanics algebra, right? With the supercharges, and we explore how and which the particles can you build with a specific graded structure.
So this is good. So you say that you are building particles. Well, the first constructing particles, better to say. So you're constructing particles using some algebra, some what you call color. It's not super algebra, right? It's a color algebra, whatever you call it. It's not really super algebra. You use some generalization of Lie algebra.
Yes.
And you construct particles, what you call particles. What do you call by particles? What's particle for you? Is it quantum field theory system, or is it quantum mechanical system? Is it lattice model, maybe some kind of spin chain? What kind of models you consider?
It's in the sense, it's quantum mechanical.
Quantum mechanics, good.
Yeah.
So then it's quite unusual, because in quantum mechanics we don't have, so it's finite dimension. Is it finite dimensional space of states, or is it something like a moving particle like hydrogen atom, where you have infinitely many states?
Sorry, can you ask again?
What is the dimension of the space of states? Can you have it in finite dimensional, or you need infinite dimensional? You need, well, I suppose you have some particle in a field, right? So I don't understand what you mean by particle in this quantum mechanical model. The quantum mechanics does not have this word particle. Well, you write Hamiltonian, and you may say ground state. Do you want, so what do you want to construct?
Well, Professor, I don't think I understand the question, but what I'm saying from particle is what kind of particle can these graded structures?
Give definition of particle.
What kind of particle?
The word particle requires definition. It's not standard in quantum mechanics. You need to define what you mean by
Or
particle.
what kind of statistics can you bring from these graded structures?
I don't understand.
A bosonic statistics, a fermionic, parabosonic, a parafermionic.
Can you give a simple example of application of this method so that I could understand it? Some specific computation, outline some specific computation, or I don't believe it's so complicated that you cannot describe it.
Example is that we did on the superconformal quantum mechanics.
Good.
With the Alfaro Fubini Furlan.
Do you have a slide already, or a page which you can show to me, or maybe write a formula?
Yeah.
Okay. So the Hamiltonian and the Hamiltonian is 526, and the other ones are what, conserved charges? They commute with Hamiltonian or not? What do they do? Okay, so for me, the only thing which makes sense is 526. It is Hamiltonian, right? This is the definition of your model.
Mm-hmm.
So the space of states on which the Hamiltonian acts is the space of functions of X, right? Oh, sorry, it's matrices, right? It's 2x2 matrices whose entries are functions of X, right?
Yes, yes.
Okay, good. So now I understand. And beta is a real number. Okay, so you have some method of working with these Hamiltonians, which you call statistical transmutation. Please briefly describe the method.
Okay, this is a specific example from this method. The method itself is before, where you try to see how which inequivalent structures that we can construct from these grid structures.
Sure.
So what kind of particle these grid structures can support in this sense, not the particle itself.
Uh-huh. What do you mean by particle? I mean, the particle in quantum mechanics, the only meaning of the particle is the actual thing which moves, right? So the Hamiltonian is p square over 2 plus v square over x square. So it's a particle which moves in a inverse in 1 over x square potential, right? That's the only meaning of the word particle which I can see here. And it has some kind of internal spin because it's actually 2x2 matrices. So it's kind of like a particle with a spin moving in a field 1 over x square. But you probably mean something else when you say the word particle.
I mean statistics.
Excuse me, Rodrigo, I think that this is not the correct, this is the correct, but you worked out explicitly the Alfaro Fubini-Furlan model. That is easier to explain, because you have a ground state, you have operator which create excited state, and then you go from single particle and multi-particle sector. So
thank you, Francesco. So I think there is a simple flavor.
Yeah.
Thank you, Francesco. Thank you.
I think you should have this, explain this, Rodrigo.
So it would be simpler than what you started to explain, right?
So we have this Hamiltonian here, right?
572.
Yes.
Good.
So you can define these creation operators and annihilation operators in terms of the supercharges given seen before.
Ah, nice. Okay, I can see, yes.
Okay.
So do they, what does index J stand for? Oh, it's one and two, right? It's 1 and 2. How about A1 commutator or anti-commutator with A2 dagger? So you have two operators, A1 and A2, right? And they're conjugate. Okay.
Yes.
Why are they useful? Why do you want them?
Sorry?
So this is one defect of the thesis, I think. You call it creation annihilation operators. But strictly speaking, in physics, this notion only exists for harmonic oscillator. This is, of course, not a harmonic oscillator. So this is some very clever generalization of creation annihilation operator. But the thing is that you cannot just use this word because it is not creation annihilation. Creation annihilation only exists for harmonic oscillator. So you should explain that I am constructing some operators in some clever way, satisfying these commutation relations, right? And why are they useful? What are you doing? Why are they useful for understanding physics or spectrum, whatever?
Because with this system, we have a discrete spectrum energy, right? So we can compare if you use ordinary statistics or
Well, there is both
modify
and continuous spectrum, I think, because particle far away would not feel 1 over x squared potential. So I think there is also continuous spectrum at least. I don't think it's only discrete. Is it only discrete spectrum?
Yes, if you...
The potential goes to 0 at infinity, so you should be able, when x goes to infinity, you should be able just to take a plane wave. And does it something wrong with that? Okay, so suppose that I concentrate on discrete spectrum. Maybe you can just, there is discrete spectrum at least. So what do you do with it? With these operators? Are they spectrum generating operators or what do they do?
So to see the influence of the gradient structures, we go to the two-particle system, right?
Okay, so now two-particle means that you consider tensor product of two such systems, right? Tensor product of two such quantum mechanical systems. So then your wave functions are functions of two variables. Is that what you mean? X and Y. One copy, two copies, and you tensor product them. Is that what you're doing?
Sorry, can you repeat, please?
Well, just definition. You're not giving precise. You're not giving clear definitions. I'm guessing what you mean by two-particle. You probably mean just the tensor product of two such spaces and sum of two Hamiltonians acting independently.
Yes, yes.
Okay, good. But then, so they don't, this is just direct sum. So the Hamiltonian is just the sum of two Hamiltonians acting on the first one and acting on the second one. It's just the sum of two Hamiltonians without any cross terms. Or do you have cross terms?
Actually, you use a coproduct construction.
No, I'm asking first about Hamiltonian. Do you consider some Hamiltonian in this two-particle system?
Yes.
What is it? It's just the sum. Oh, it's 597. Fair enough. Good. So it's just the sum of two, right? They are not in any way, there are no cross terms. It's just sum of H DFF acting on the first particle and H DFF acting on the second particle. So these two particles are kind of, there is no interaction between them. In principle, you could have considered some interaction Hamiltonian, but you're not doing that.
No, no.
Okay. So why are these coproducts? Okay, so what do you do with these coproducts? Can you tell me, before you consider two-particle system, on one particle system, do this A and A dagger act on a vacuum in a specific way, like for harmonic oscillator, A annihilated vacuum? Is something A annihilates vacuum here also?
Yes.
Okay. And A dagger generates spectrum. If you act with A dagger many times, you get spectrum.
Yes.
Okay, so far so good. But okay, excellent. 100, I understand. Although, wait. I don't understand. What do you mean delta of A1 and delta of A2? But I would say that the vacuum should be just tensor product of two vacuums. So not only delta, but A1 first. So A1 acting on the first system, and A1 acting on the second, and A2 acting on the first, and A2 acting on the second should all be zero. Not only coproduct. Coproduct is too weak. Why can't I just take the tensor product of two vacua?
Well, we use this vacuum here, right? So the coproduct encodes the action of the.
But 98, notice that 598 is very interesting. Namely, it is just a product of function of x and function of y. And function of x is the vacuum of the x system, and function of y is the function of the y system. So it's like x beta times e to the power 1/2 x squared. So it's just the product of two vacua. So it's not only the coproduct which annihilates it, but actually annihilation operator of x, annihilation operator of y separately, not only their sum.
Rodrigo, sorry, I think that you are tired because you explained this in your thesis and also in the presentation at the beginning.
So what I'm saying is true. That is it true?
Look, by the way, this is a system of harmonic oscillator, or if you want, a matrix harmonic oscillator.
Well, it has 1/x squared term. Is it still harmonic oscillator?
It's a deformed harmonic oscillator. You can put beta equals 0 and you have harmonic oscillator. That's not a problem. That is not the point. But the point is the following. You construct this algebra is a spectrum generating algebra.
Good.
For the single particle system. So you have this creation operator, which generates from the vacuum all excited state.
Good.
After, and this is explained at the beginning, you want to go from this to the multi-particle system, non-interacting multi-particle system. you can do that.
Right.
And then you know that when you do this, it is not a detention product. You have to consider the symmetrization or the anti-symmetrization of the wave function.
Well, I can consider
And this,
the Young symmetrizer. I can consider, well, in case of two, yeah, you're right, sorry.
the tool to do that is one possible tool is, as pointed out by Majid, is the coproduct, because gives symmetrization, anti-symmetrization, and can be generalized for other type of statistics. And that's why he's focused on that.
Okay, so now I think, well, Francisco, I am starting to understand what you are doing. I'm having a dilemma that it is you who are telling me this and not your student.
I think he is tired because he knows very well that. He knows
Very well.
Yeah, sure.
Okay, then, so when you go in two, you don't have any transmutation. When you just have two states, you don't have any transmutation, I understand. So it starts with three or something?
Rodrigo.
What do you mean by two what?
Can you explain to me this phenomenon of statistical transmutation on this example?
Yes.
So what happens?
Okay. From this two-particle energy spectrum, right? We use the coproduct. Use the coproduct to construct the excitations of the stereo. So at the second level state, you have the influence of these gradient structures in these terms here, this delta, right?
What is delta?
So delta is depends on the relations of commutations and uncommutation relations given in here.
Is it true that delta are just numbers? These three numbers?
Yes. Take his values plus and minus 1.
Okay.
So from the gradient structures, we can count. We can see the different combinations of this delta in different gradient structures, right?
So what?
These possibilities of gradient structures.
In quantum mechanics, to this different, is it you consider different states for each choice of three deltas? You consider different states. Can you explain this?
Sorry, can you repeat?
Well, before you go to this table, how does this work in terms of psi of x, y? In terms of wave functions, what happens? Or in terms of quantum mechanics, what do you do with, we took tensor product of two particles, I got that, and then what do you do? You construct delta, sorry, what is Z? Z is this matrices, okay, so these are not trivial operators. Oh, Z and V, this. Okay, so what is your purpose with this delta? What do you want to do with them?
So you apply this to the
vacuum?
To the vacuum, yes.
And
we count the energy excited states, right? But we have the influence of the gradient structures in these terms here. That depends on the commutation and commutation relations, right? So from the algebraic statistical transmutations, you count all the possibilities that.
Okay, now you are ready to give me the definition. What statistical transmutation is? What is statistical transmutation here?
it's a way to see how many inequivalent statisticals can emerge from these graded structures using the super quantum mechanics operators.
So as Francesco pointed out, you could have done it for harmonic oscillator, right? So I don't have to bother about. So you can take, so it's in principle, it's a textbook problem. In the tensor product of two harmonic oscillators, you are saying that there are subspaces, right? I'm a little bit, so you don't take arbitrary state psi of xy, but you impose the condition that it is, at first you could say that it's either symmetric or antisymmetric. But I suppose at higher levels you can consider, what is it exactly that you are doing? I can consider symmetric and antisymmetric. I can consider wave functions which psi of xy equals psi of yx. Or I could have vice versa, psi of xy equals minus psi of yx. That we all know. There are such subspaces. You are saying that you can do more, and I'm not grasping it.
Yes, if you go to the second excited state, for example, you have more possibilities of these from these parameters here. So
So,
at
harmonic-
one level state,
I see.
you cannot differentiate. I agree, but from the two level excited state, you see a difference coming from this degraded structure.
Okay, we are coming close, but I am still. Can you do it at the? I understand that you need two oscillators, A1, A2, right? So you cannot do it just for one. Yeah. But that's.
Rodrigo, I think you can even explain from the ordinary harmonic oscillator.
Yes.
Because for a ordinary harmonic oscillator, you don't have parastatistics, you have only two possibilities, bosons or fermions. You start from a single particle harmonic oscillator, you have one creation operator, period. And then, once you have this, you construct a multi-particle state. Rodrigo?
Yes.
So, I try to explain where, in which sense you call this statistical transmutation.
Well, he starts with two-dimensional oscillator, right? Because there are A1 dagger and A2 dagger, and they have the same energy, right? So it's kind of rotationally invariant, the U1 invariant, the one where two frequencies are the same.
Andrei, sorry, if you want to understand the notion, you don't need to go to two-dimensional.
Oh.
You just take a single harmonic oscillator, which depends only one space coordinate.
That's better.
So the creation operator is defined, and the Gaussian is the vacuum state. Now the question: what you do when you want to go to first from single particle to multi-particle state? This is called first quantization. So You
It's
have
just
two possibilities
it's just
for
tensor
the
product.
same operator.
Uh-huh.
You can consider as a boson or consider as a Fermion. That's the point. It depends on the sign which enter the coproduct.
Yeah, it's because in tensor product you can consider symmetric and anti-symmetric tensors.
Right, that's right.
Uh,
But if you start from a more general framework, like this, you need at least two. You can have more possibilities because you can introduce these parastatistics, not just bosons fermions, but these 6 cases, which are consistent for the same set of operator.
Can you ask him? Can I ask him to give a simplest? So there is absolutely no way he can write it, or just the simplest example of Rodrigo.
Rodrigo,
Okay.
Falling asleep.
write the simplest example, or show the simple example.
But I want in simple terms, in terms of oscillators, which I understand now, not in this data product. Product I don't understand. Can you explain just writing like people usually do in quantum mechanics? You just tensor product and you act on the first one, you act on the second one, and
Okay, Rodrigo, 583 was okay. It was the vacuum state,
Yes.
single particle vacuum state.
Mhm.
And Rodrigo, you're there.
Yes.
Show 585, which tells that
Mhm.
The relation of the
liquidation operator.
Two-dimensional harmonic oscillator.
Yeah.
There is A1 and A2, but okay, whatever. Okay.
It is not a two-dimensional. It is a matrix harmonic oscillator. Depend only on one coordinate, x.
Oh, I see.
Rodrigo, you have a formula. You can a formula of the state. 586. Sorry, I mean I think you're tired.
Yes.
Yes. Okay. Okay.
Rodrigo, you can read your sentence of 586 because it is.
Well, I see it. I got it. I got it. This one I got. Yeah, please go ahead. Oh, so I registered 586.
So you apply this the Hamiltonian to the states, right? And you have this as the eigenvalues for the energy levels.
Mm-hmm.
And on beta, M, R, and S,
Mm-hmm.
right?
Mm-hmm.
Okay. Here you separate the vacuum. The vacuum energy is given here. So above that you have this spectrum, energy spectrum.
Mm-hmm. Twofold degeneracy because of the matrix harmonic oscillator.
Yes, from the first excited state and so on.
Mm-hmm. Okay, please tell me, the matrix harmonic oscillator is just tensor product of harmonic oscillator with spin 1/2, right? With two-dimensional space.
Yes.
Mm-hmm. Okay, very nice. And then you are saying that
Now, Rodrigo.
Yeah, I think I started to understand.
Show how to construct the two-particle state from these, which is okay. So
okay, for two-particle state, use the Hilbert space to in this tensor product here, right?
Mm-hmm. Yes.
but it is a subset of the Hilbert space of the tensor product.
Mm-hmm.
Use the formula that you have there, Rodrigo.
So it somehow mixes the matrix degrees of freedom with so you cannot do it for one-dimensional, right? You really need the spin degree of freedom, the two-dimensional space, in order to have some braiding matrices. That
if you want to have parastatistics, yes.
mm-hmm.
If you want just to have bosons fermions, you just can do for a single oscillator.
No, I would insist that in the revised version of the thesis, he gives simple example of parastatistics in normal terms, without co-multiplication, just in pedestrian terms, in usual quantum mechanics, for a harmonic oscillator. And I would insist on that. And there is another thing in the thesis which I want to insist. It's on page. So there is a last section. Let us talk a little bit about it. Applications in quantum field theory. This section is unpublished.
Yes.
It's true. So I'm not sure if rules allow to include in the thesis the unpublished material in this form, because it's substantial part of your thesis. So, and am I supposed to be a referee? I'm not sure. Please double check with your department if this is allowed. But in any case, I absolutely insist in 6.2.1, there are two strong statements. Like in summary, quaternionic field theory offers mathematically rigorous and physically compelling extension of standard quantum field theory. I am not ready to sign under this statement, because if I approve your thesis, it's like I approving what you are saying. I'm not sure if I believe that it's an interesting idea, but I'm not sure if it is completely sound and rigorous mathematically. I can't sign under it. So I can only approve if under stipulation that you remove such sentences. And even better...
Andrei, which sentence? Just a moment. Which sentence? Could you repeat?
6.2.1, motivations for quaternionic representations. In my copy of the thesis, it's on page 68. Well, I'm not sure if I understand this quaternionic quantum field theory. Although I understand that there is a paper of Giardina, but I think it's more on the level of ideas. So maybe Sergio can comment. I'm not familiar with it. So either you give me more time, or you promise me, or we stipulate in the report that you remove the statement. I do not agree that. I'm not sure if I agree that quaternionic field theory offers mathematically rigorous extension of standard quantum field theory. I'm not ready to judge it. Okay.
Okay.
Here, I'm sorry. Here we also cite a paper which was published, by the way, this paper 81. That's some that's already the method is the same anyway. But okay,
yeah,
understand your point.
Yes, I forgot. While we are at it, the third major defect of the thesis is that there are very few references in line in the text. Very few references, you know, the side comment in LaTeX, the citations. And in particular, it is very hard to say which part of is review and which is your original result. So you should, so this is absolutely necessary to clearly mark which parts are your original result. And if it is not your original result, then you should put a citation. Because there are so many places, I won't even run over them, there are so many places when you make non-trivial statement in the paper without either explaining it or without either saying that it is your result and how you got it, or you should cite the paper where you got it from, if it is not your result. Sorry, Francisco, I interrupted you, but you are saying that there was already, besides the paper of Sergio, there was your paper, or?
No, the paper with the paper of Jana, and with her student, who is now. So they analyzed a non-relativistic model, and this work in progress that it is the first one on relativistic theory. Is we planned to finish before the thesis, but okay, as usual, there are something more. But we had a similar result as this what he mentioned concerning this formula that he showed before. So,
well, I think
versus parabosonic, there is a difference in the interaction term. That's the point.
Okay, so I would insist on removing strong statements, because relativistic is very different from non-relativistic, and I don't have time to...
Yeah, I understand.
Okay, so that's it. I don't have any more comments with this.
Okay.
Okay, thank you, Professor.
Thank you, Andrei, for all this comment. So, concerning the discussion, so I have some comments about what was asked by various professors. So just one point concerning a question of Joris van der Jeugd about these 6 different cases. You have 6 different algebras, superalgebra graded. Some of them are finite generated, and some of them are infinite number of generators. But the universal enveloping algebra that you obtain, it's always infinite. So that's why it is easy not to remember which is the 6 cases finite generated or infinite generated, because at the end you always use the universal enveloping Lie algebra. Concerning question I put by Professor Giardino, I would like to ask him the references that he mentioned in the 60s, because Rittenberg-Wheeler is the first work that introduced this Z2Z2 parastatistics, Z2Z2 color algebra. There is a previous reference. Sometimes it is quoted in the literature. In our paper, also paper by Van der Jood, not always. There is in Canadian Journal of Mathematics in 1960, there is a read that introduced a structure which are of this type. But then everything came after Rittenberg-Wheeler and Schoenert. Mathematicians like to refer Schoenert. Concerning the question of color algebra, I think that at the beginning, Rittenberg-Wheeler, they wanted to apply to quark. That's what they call color. And I learned from Professor Van der Jood that we should always put the term color algebra because of it is not ordinarily algebra and ordinarily superalgebra. And in order to avoid misunderstanding with mathematicians that they classified the two n-graded structure for the algebra, we should always mention if it is color algebra or color superalgebra. This I learned from Professor Van der Jood. So, I really think Professor Pinzul for all the nice observation. I agree with him about that. So implication, and then with the question of put by Professor Mikhailov. So I want to mention something because there was some point that has been put forward. So Rodrigo gave a absolutely important contribution. So he pointed out the existence of Carnot map, and that this kind of systems could be realized in terms of Boolean logic gates. In a sense, this is just a reformulation of the theory, a reformulation of the algebraic structure. But this reformulation can be quite important for practical application. Because if one has Boolean logic gates, in principle, we don't know yet, but this could be used as a blueprint to for experimentalists to conceive some way to engineer paraparticle in the laboratory. And in fact, we had some mail exchange on that with a group of Huerta Aldereta. Some other point that was asked by Alessandro Pinzul about in this particular example, we don't have a real control parameter. Everything is discrete. So we have this sort of possibility to engineer the structure via this kind of Boolean logic gates. And this is a hot question because we know that we have these theoretical models, toy models that is possible, but we don't know yet. No one has yet performed experience in the laboratory to detect them. But I think it is quite possible to do that. I want just to mention that Rodrigo, so the paper that was published is a very big paper, was contained a lot of information. We worked out the structure of first starting from the set of operators that satisfy some grading, and then which kind of color algebra, superalgebra are supported by this. That's the point. And this was a big investigation. Rodrigo gave a great contribution, including with packages, Mathematica package, Python packages, to check a lot of these ideas. And you have seen probably all this diagram in this thesis about all subalgebras that was done well, entirely by Rodrigo. And so, and that was quite a big job. And concerning the other part, yes, it is true that has not yet been submitted. It is a work in progress. Will soon be set. But this is the first example of application of a relativistic system with this kind of structure. And some of the results are already there, like it's work in progress, but the consistency of spin statistics, because so far nothing has been done in the literature concerning this relativistic system, only on the level of non-relativistic system. And also this, we have this kind of investigation done with Rodrigo that focused on this point. I should mention that in all time, there was just one example by Misha Vassiliev that in 85 introduced de Sitter supergravity and pointed out that using this color superalgebra solves some problem of the notorious problem of defining supersymmetry in the Sitter space. Some of the problems are solved, but no systematic investigation. So that's really the very first part on that. So, and Rodrigo gave a really great contribution on that. So, so now I think I can. Is all what I want to say, and I should ask Larissa probably that we should start the question and answer session. Sorry, the deliberation of the commission.
Oi, Tupã. Só
Oi,
aceitar na
Larissa.
tela de vocês, tá?
Como?
É só aceitar na tela de vocês que vai aparecer uma perguntinha para vocês mudarem de sala.
Okay. To everybody. So I don't see
so
anything.
we just click join, right? I mean, we have to join.
This is join. Okay. Yes. I'm here. Hello? It worked. Just a moment. Hello? Can you hear me? Okay. Okay, so good. You can hear
Tupã,
me.
você ainda está nessa sala aqui. Você tem que transferir os dois.
But I cannot see, just a moment, I cannot find the join in my.
Ele não está me vendo. Ah, tá.
It was also necessary to they stuck in the breakout room.
Okay, Francesco. Okay, so he's here.
Mm-hmm.
Yeah. So, yeah,
Okay.
Rodrigo is also here, so everybody's here. So, okay.
So, participant, everybody is here. Just a moment. Okay. So, okay. Larissa?
Sim.
Are you there? Yeah. So, I think we can communicate the result. Hello?
Oi, oi.
Mm-hmm. So you will explain after what to do. So I will tell Rodrigo. Hello, Rodrigo?
You should say something.
I'm here. I'm here.
Are you there?
Yes, I'm here.
Okay. So it is my pleasure to tell that you have been approved by the member of the commission. So we agreed, all of them. There are some suggestions for modification, but we know that for the thesis, for the final version of the thesis, and Larissa will explain when this should be done. And so all professors will give some of the suggestions were already mentioned during the presentation, but okay, the commission approved, all the members approve. So congratulations.
Thank you.
For
And
this.
parabéns, congratulations.
Congratulations. And Larissa, you will explain us what to do, because you have to sign some document that you will send now after. How does it work?
Ok.
Yeah. Okay, so I guess it will be some electronic signature afterwards, right? Or something like that.
Yes.
Okay.
I think so.
Okay, so thank you
Larissa?
very much.
Oi.
Oi. How should we go now? You will send us some document to sign.
Sim, yes.
We will
Okay.
receive it by what? By email or something?
Não, Paulo, não tô compreendendo. Pode falar em português, por favor?
Português, yeah.
I cannot hear.
Ele está perguntando qual é o procedimento. Você vai enviar algum documento pelo e-mail ou como?
Isso. Eu mando a ata por e-mail e vocês só assinam. E pode ser assinatura do Gov, tá? Quem tiver.
Ok.
Certo.
Mas,
Okay.
só vamos esperar nesse caso.
So now, for everybody, this was a long discussion. Thanks for everybody for this. So we will we will receive a document to sign. So we agreed. Congratulations once more to Rodrigo, and thanks everybody. Thanks Professor Banderio. Thanks Professor Giardino. Thanks Professor Pinzul and Professor Mikhailov. Okay. So, and we will wait for the document from Larissa to sign this formal acta of the commission. Okay.
Okay.
Thanks. Congratulations again. Good luck.